Hi. In the last video, I completed the control logic midplane. Today, I want to get into the reset circuit. There are several things that need an extended reset in order to complete, the control logic midplane being one of them. And so I need to hold the circuit in a reset state for an extended period of time. Several things need to happen during the reset, and so the entire point here is to make sure that the entire circuit comes to a known good state before I start executing code. I have some thoughts about what I want to do and how I want this to work. I know I have some requirements, and I'll get those listed out. But I'm going to try a top-down development approach in KiCad and see how that works out for me. I'm kind of making this up as I go along. I'm not sure if this is best practice or not, but join me as I go. Let's get into that. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. My wife Carrie has been working on a cookbook. Carrie's cookbook provides a unique culinary experience by seamlessly incorporating doTERRA essential oils into a diverse array of mouth-watering recipes, transforming ordinary meals into extraordinary dining adventures. The cookbook offers a treasure trove of innovative dishes that combine the health benefits and aromatic richness of essential oils with fresh, wholesome ingredients, making gourmet cooking accessible and exciting for everyone from novice home cooks to seasoned chefs. Each thoughtfully crafted recipe not only tantalizes the taste buds, but also promotes an overall well-being, harnessing the natural potency of pure essential oils such as lavender, lemon, peppermint, and basil. In Carrie's cookbook, she emphasizes the quality, flavor, and simplicity, guiding you through detailed, easy-to-follow instructions with beautiful photography and expert tips. Whether you're looking to elevate your everyday meals, explore new flavor horizons, or embrace a healthier lifestyle, Carrie's cookbook is your ultimate guide to enriching your kitchen and your life with the magic of doTERRA essential oils. If you are interested, there's a link in the description. Like I mentioned in the intro, this top-down approach for circuit design is something that's going to be new to me. I definitely am familiar with it in developing code, but my go-to is typically a bottom-up approach, not a top-down approach. I think this is going to help me develop something that actually works a little bit easier because I can take a completed concept and then break that down into components that are going to hopefully work all in conjunction with each other. And so what I want to start off with is a list of things that this reset circuit is required to do. The goal is then that list of things that it should do will then lead into a block diagram, which then I can drive into specific detail. All right, let's start with the things I need it to do. First of all, I am not going to distinguish between a hard reset and a soft reset, so this is going to be triggered either by power on or me manually resetting the circuit, and then everything should reset back to a known good state. While the circuit is in reset, the high-speed system clock needs to be presented to all components, and that is to make sure that everything has an opportunity to latch the contents as quickly as possible. We want to drive that as fast as I possibly can. The control logic midplane being one of the most significant of those, that's going to take the longest to perform a reset. So I want that done as quickly as possible. I need to make sure that I drive that change to the system clock and then back to the CPU clock using the proper timing. So I'm going to have to latch that changeover and make sure that it's happening appropriately so I don't have these little teeny tiny slivers of clock cycles. I want to make sure that any component can assert the reset hold. Now it's an active low and open drain right now on the control logic control module. So I want to keep that consistent. But anything should be able to hold the circuit in reset until everything is ready to go. Finally, I want to be able to allow for some number of additional clock cycles after all the modules report in that they're ready for execution. This I am expecting to be required in order to facilitate that transition from the high-speed system clock back to the CPU clock. That count may be 1, it may be 7, I'm not exactly sure what it is, but I want to design that in now rather than coming back and adding that later. Now, I believe this is a reasonably comprehensive list. I may end up having to add something as we go through this design. Certainly, I have not taken any of the pin ins and pin outs or interface points into account yet. So as we get into the block diagram, we'll have to look into those as well. Okay, Adam, how are you planning on doing this top-down design? And really what I'm going to do is I'm going to start pulling in some hierarchical charts or sheets. And so, for example, I'm going to stick one here. I need a circuit to handle power on reset. I'm going to need another sub-circuit, if you will, to handle manual reset. I'm going to need a sub-circuit which handles the clock selection and timing. And I'm going to need something to handle the post-reset. Now, I may or may not need this, but I'm going to throw it on for now, and that is going to be something that's going to be a state. So I'm going to need to be able to track whether or not, similar with the control ROM control, whether I am actually actively resetting, whether I am in extended reset where something is holding the system in reset, or if I'm in normal run mode. Now, I may be able to determine that from signals, but I want to throw this in here just so that I have it at the high level. From what I can tell so far, that is everything I need from a blocks perspective. The next order of business is going to be to define that interface. Next on the block diagram, I want to take a look at the external interface points. The most fundamental are going to be power and ground. And then let's start looking at some of the other things that we need to be able to interface to this reset circuit. I need as inputs both the system clock, that's going to be an output off the interface, and then I also need the CPU clock. And then as an input to that interface, I need what I'm going to call a reset clock. That's going to be an input to the pins. I need an outgoing reset signal, and that one is active low. I also need a reset hold. That's going to be okay, so reset will be an input to the pins. Reset hold will be an output from the pins. And then I think I need 3 pins which are going to be resetting. Actually, 2 additional pins. Resetting, and that's going to be an input to the pins. And then I'm also going to need a running. And the reset, resetting, and running are going to be the 3 different states that I can look at. So that said, let's get a pin header. And on this, I will put the different clocks and add some ground references and the like, and get this all cleaned up so that it looks reasonable. The next challenge, and I'm not sure how close I'm going to get the first iteration here, is to map all of the communication signals between each of these blocks. For example, if I go into the power on reset, it's going to have an output that is going to be the reset signal. And that's just going to be one of the outputs coming off this particular sheet. Now, if I go back to the top here, I will have a reset coming off there, which will then end up going to this particular reset, which is going to be an output coming off that hierarchical block. And now I'm going to have the same thing for manual reset. It's also going to generate a reset signal that then needs to be handled. And then my state needs reset as an input. Does the clock selection and timing need the reset signal? Yeah, I believe it does, because it's going to actually switch the clock from the CPU clock to the high-speed clock. And do my post-reset clocks need reset as an input? No, it does not. My state has outputs that are going to be resetting and running, so let me get those added. What is going to trigger the clock selection to switch from the high speed back to the CPU clock? And that's going to be transitioning to the running state. Or is it going to be coming out of reset hold? So reset hold needs to be an input into state. So reset will trigger resetting to go high. It will remain high while reset hold is low. When reset hold comes back high, running will then be triggered back high. Resetting will go back low. All right, I think I got that right. The clock selection and timing is also going to be dependent on reset hold. I wanted to go to the high-speed clock on reset. I wanted to come off the high-speed clock when reset hold comes back high. So that's going to be an input. Okay, the next thing that needs to take place is some communication between my clock selection and timing and my post-reset clocks. And that has to be based on latching the fact that we are out of resetting and getting ready to clock the CPU forward once or twice. I'm not exactly sure what to call that. For now, I'm going to call it just simply post. And that's going to be an output off of this one. And then I'm going to have an input here, also called post. Inputs and outputs, I need a system clock input, CPU clock input, and then the reset clock output. The last thing I think I need is some bit of communication between my post-reset clocks and my state, which will trigger it to go to running. This is now, in effect, what I believe to be the block diagram of how I'm going to make this work. Okay, let's get into the details of manual reset. Now, since this works well on the breadboard, I'm just going to lift it straight off of there and copy it straight into the schematic. And then this is going to go to ground reference. And it is quite simply as simple as you push the button and it pulls reset low. Now, there is a challenge here in that reset needs to be tied high by a resistor. And I'm going to do that on this sheet. And I think a 10K, but I'm going to have to play with this value a little bit. A 10K pull-up resistor is going to be just fine. So the details of this are very simply, reset is pulled high external to this subcircuit. When I push the button, it pulls it hard low and puts the entire circuit into reset. And that's what I wanted to see happen. Okay, next is going to be the power on reset. Now, I had to create the LP3470 that I'm using in my circuit. And the trivial connection here is for pin 5 to be connected to the reset signal. Again, VCC and ground ref. Now what's left is a small capacitor. Let's see here, that capacitor is tied to ground and it becomes the timing capacitor. This is going to be a 0.1 microfarad capacitor. Okay, that then is the power on reset module. And that's very much like what I have on Breadboard today, again. Now for the more difficult ones. Next, I think I want to get into the clock selection and timing. And so I've got two different clocks here, the system clock, the CPU clock, and an output is going to be the reset clock. Trying to think this through a little bit here. Ultimately, what I need here is a 74HC00 so that I can create what is quite simply just a set reset latch. So here I've got the connection from one now the output of this needs to be ANDed together. So that's an 08. So when I'm in reset, I've got the system clock. When I'm in out of reset, oh, I need to invert this. Let's do that with a spare NAND gate. When I'm out of reset, reset hold will go high. I need that to then turn low, which will hit this, switching me back to the CPU clock. Finally, I need a 74HC32, and then I've got a few extras. And there's my reset clock. Now, I don't believe I need this post signal anymore. I believe reset hold can do that and start that process on the... I was going to have this clocked and latched. I don't think I need to do that, at least not here. So I can get rid of post there, and I'm hoping that these can all come back to the main without actually changing their identity. So this is U2 and this is U2. Okay, good. Now the last thing I need to do is I need to duplicate this for reset hold because I do need to have a pull-up resistor on that signal as well. So this will be there, that'll go away. I believe this is going to now be reset hold. I also am going to need the CPU clock in here. Okay, I think that cleans up my clock selection and timing and tees up my post-reset clock counts nicely. Okay, the next thing I want to take a look at is the state. Now, for that, I really only need, I believe, so let's see how close I can get, is reset and run. And again, this will be implemented as a set reset latch. And once again, I do need to invert that signal. So I'll use one of my spare NAND gates. Okay, so I don't need the reset hold. I can remove that. And then these two, I want to relocate back to the main sheet. Reset hold, I don't need there. I don't need reset hold there. Okay. Okay, the last block to flesh out is the post reset clock clicks. Now for this one, I'm going to need a 74HC193. And I want to load that with some value, which I'm going to define with a 4-gang dip switch. Let's see if I can what I can find for that. All right, so single pull, single throw. Okay, let's put VCC on here. I'm going to need that in several places. Let's go ahead and put ground on here. Now I will admit that I am actually using what I've got on the breadboard as reference for this as well. And then I will doctor that up a little bit. The outputs of the counter I actually do not need, so I will mark those as unused. Carryout I'm not going to use either. Okay, these are all tied directly to VCC. Each one of these are tied to ground on one end. The other end is tied up here to the other side of that switch. These are all 10K. And each one of these lines feeds into an input. So I can specify now the number of clocks that I'm going to use in order to manage the post reset clock cycle. Reset hold should be able to drive my load. And so as long as reset hold is low, meaning I am resetting, it is continually loading. It's asynchronous, so it won't actually start clocking until reset hold goes high. That's appropriate. My CPU clock is tied to the up count. So every time it ticks, I should be counting up. No, that is incorrect. That's going to be tied to the down count. Up count needs to be tied to VCC. So I'm counting from whatever this counter set is down to 0, and clear should be tied low. Now the last thing here is the borrow out, which then becomes my run signal, except it needs to be inverted. Let me pull in one of those inverters. I'll go ahead and invert this. I may regret that. So the thinking here is, if I make run an inverted signal, then I don't need this inverter here. It'll save me a gate, but it doesn't save me an IC. So where do I invert it? Do I invert it here? Do I invert it there? Where else is run used? So run is really between these two blocks here. All right, let's just get rid of the extra gate. Make that an inverted signal. So it goes back to run when borrow hits 0. So I'm going to be short one cycle. So it's not counting down to 0, it's counting down to 1 effectively, and then it goes into run mode. So the question is do I need to put a latch on the other side of that? That I might need to do. So this now changes this to be an inverted signal. And then in here, it gets rid of that. I shouldn't have deleted that. I needed to cut that and paste it over here. Yeah, I think I want to add a latch to this. So this is going to be a 74HC74, which I only need one of. These are explicit set and reset. So let's see here. I don't like the 4-way connection. But what I'm not certain about is, do I need to invert one of those clocks? Actually, the better choice here is going to be to add a set reset latch in here. So let's go collect a couple of NAND gates. 5C and 5D. I'll use those. Okay, reset hold should be able to set this particular one high, and then borrow out should be able to perform the reset. So reset hold goes low. That is going to trigger the set part of that, which will make this output a 1. And then as it clocks, it's going to latch that 1. When borrow goes low, it's immediately going to change this to be a 0. The next clock step then would latch that 0 and turn that to running mode, again being an active low signal. And that then also provides some additional protection from the counter, which is going to continue to count. I don't have to do anything to actually stop that from counting. The set reset latch provides that isolation. Nice. Before I start running the electrical rules check, I do want to spend a minute here and do some cleanup on this sheet. I've got to get power and ground settled in here so that I can get everything properly hooked up here. Okay, this looks reasonable. Let's save this and find out what it doesn't like. Well, it doesn't like the fact that I have renamed this run pin. That wasn't it, was it? That was it? No, it pulled in an incorrect definition here. So that's what my problem was. Let's build this in the emulator. So this appears to be working, but there's a problem. As this gets close to the end of its copy, it actually is starting to execute code, if you will, while it is still in reset and supposedly counting the CPU in order to clear everything. That's not desirable. What exactly is it that is the problem? And that's going to boil down to this reset hold signal and making sure that this reset hold is being input from the control logic midplane, but also output to prevent the rest of the CPU from executing code. Now, as I go through this and look at this, there are a few issues that I have managed to uncover that I really kind of need to talk my way through. So in my state, I am accepting reset hold as an input here into a set reset latch. Reset hold is actually also causing the counter to load, and that happens asynchronously. So the problem is that while both of those are accepted as inputs and driving the conditions, if I was to also output onto reset hold, which is what this would be, this now becomes a circular dependency between here and these two signals here, meaning I'll never get out of reset. Well, what's the solution? Well, ultimately, in thinking my way through here, I need to be able to track my way through 4 different conditions or 4 different states. I need to actually track the reset state itself when I'm actually pressing the reset, or the power supervisor, voltage supervisor is actually holding the circuit in reset. When I'm resetting, which should be when I'm copying the SRAM into the EEPROM for the control logic. When I'm clocking the CPU in order to clear things, and then finally getting into the running state. Let me get KiCad back up. I will reset my state and make sure that that works, and then this is likely going to have to change as well. Back when I was looking at the 4-cycle clock, I needed some way to toggle back and forth between a run state, a single step mode, or a single clock cycle. My single step being one of the 4 different states of the 4-cycle clock I was looking at. Now, I'm not coming back to this, but what I am coming back to is this circuit here. And this circuit was designed so that if I pushed one of 3 buttons, one of 3 different states were going to appear. If any one of them was set high, the other 2 would automatically be set low. So if I hit single step, this line would come high, the other 2 would come back low. I want to leverage this and put this into my reset circuit in order to track what state I'm in. You know what? Let me get into Logisim Evolution. I'll show you what this does and how I believe that this is going to help me. Okay, so here's that circuit in Logisim. And each of these push buttons here on the left are tied high, and then when you push them, they go low. And you can see that with the light green versus the dark green. And so these are all 3 lights mutually exclusive, where if you push one, the first light turns on. If you push the second one, the second light turns on. If you push the third one, the third light turns on. If I was to call this reset, if I was to call this reset hold, because I have no better term for that, and I would have to invert this coming in, and then this one would be my run signal, which I have on the board now. The output here, this would be resetting, this would be the clocking, and this one would then be running. And that would be how I would be able to track the 3 output states, but the 1 input state also coming in. The reset would trigger the rest of these in turn. So resetting, once I got the confirmation back from the control logic midplane, I would be able to go into my clocking mode. Once I got done with clocking mode, I would then be able to go into my running mode. Now there's a problem with the reset hold and with the run. So let's start by getting this much into KiCad, and then I'll come back and address reset hold and run. Let's talk about the high level. The first thing I think I want to go after here is the interface points. There's reset, which is a signal heading off to other pieces. There's resetting, there's running, but I have now added another possible signal here. And so I want to move a couple of things around. So the one that I'm getting from the control logic midplane, I want to rename that and call that copy hold. And then I'm going to produce an output for everything else called reset hold, so that this circuit then translates copy hold into reset hold properly. So it will hold everything else in reset until all of this work is done. On my state, I've added a third state that I need to include in here now. This is going to be an output, and this is going to be clocking. I also need to bring reset hold into this circuit, and while I'm at it, I'll rename it across the entire schematic. So now I just need to get that circuit pasted into here and get it working. That's reasonably cleaned up, and that's the same circuit that I had in Logisim Evolution. But I also have a bit of a problem, because when copy hold is completed, this signal goes high and remains high. I need to invert it so that it goes low, but the problem is I need it to go low and pulse back up. I cannot have it go low and remain low, because if it does that, then it puts this circuit in an undetermined state. I have the same problem with the run circuit here. Now I asked ChatGPT about this, and the suggestion came back to use a 74LS123 multivibrator. I've never used one of these before, but I went ahead and looked it up, and I happen to have one. And it looks like, based on the sample circuits here from Nexperia, this should be relatively easy to hook up. There are 2 on a single IC, and it does come in an HC version as well. So I'm going to paste this into the schematic and wire it up the way I think it needs to be. My challenge now is going to be how to emulate this, and that should be not horribly difficult to do, I hope. So let me wire up the 74HC123 into the state subcircuits, and then we'll figure out what's next. Okay, that looks like it might be reasonable. The only challenge is that I am told that there may be a pulse on power up, so I need to take this reset and define this reset with a capacitor and a resistor in order to hold reset. Let's see here, gotta hold it high. So that should work, is what I'm to understand here. Now run is also a high going signal that I need to just trigger the multivibrator with. Now, at this point, I've just guessed at the resistance and capacitance values in here. I'm going to have to put this on a breadboard and kick it around a little bit and just make sure that it's going to behave the way I want it to. But that's what prototyping is all about. Let's do some final cleanup here. I did make a mistake, so I do need to correct that. And that is on this pin here needs to be tied low, not high. So I will make that change, and then that gives me the opportunity to better center VCC here. And then I need to do the same down here. Now let's pull this and put it on the main page. Now I have in my notes that I am missing a capacitor for one of my ICs, and so I just need to make sure that I've got the right number of ICs and capacitors here. So my highest number IC is U10, 8, 7, there's a 6 somewhere, 5, 4, 3, 2, there's a 1 somewhere as well, or there should be. So I need 10 capacitors. That'll solve the issues from the electrical rules check. Okay, so run is actually an active low signal. I need to change that multivibrator. I missed renaming some of those reset hold signals. The next thing to do here is to figure out how to generate the reset hold signal from this circuit. What it boils down to is as long as we are not running, we are in reset hold. For that, I'm going to use a 74HC03 open drain NAND gate and use that as an inverter. All right, let's check this one more time. Clean. Well, debugging the code has revealed a few issues that I think I need to address here. The first one here is I actually need an LED to indicate when I'm in resetting. And that is going to be based on this running signal, but I need something to drive it with. And I figured I'd just take one of these OR gates and use that. I have two signals I need to shape coming off of the vibrators. For that I need, or ideally need, two NAND gates. I've only got one available here. But I am using one as an inverter, and if I take a NOR gate and come over here and place that NOR gate here, this then provides the same signal, but I get to reclaim a NAND gate for use with the other signal I need. Now this is decorated incorrectly, so let me correct this. This is NOR 1Y4. And then I need to now go get that change in the code and make that change there. Page 5 has an error on it, and this signal here was supposed to be connected there. Now that will be inverted Q1. And then finally in state. Now here is a rather significant change that needs to take place. And I need those NAND gates that I just freed up. All right, both of these are going to take as inputs one of the inputs will be the reset signal. The other input is actually now going to be the Q output. It occurs to me that I didn't explain why I needed these NAND gates. It turns out that on reset, I am getting some spurious signals out of those vibrators. And what I need to do is I need to filter those out so that while the circuit is in reset, those signals will not actually make it through and instead will be trapped and held off. It appears to be only during the reset, and I honestly am not sure if this is something that's going to be absolutely required in real hardware, but we'll test that next video. Okay, let me make that change in code. Now I just have to clean this up a little bit. Back to debugging. Well, it took me long enough to realize this, but one of these things is not like the other. And when I transposed the circuit from Logisim Evolution into KiCad, I did it wrong. And I've been chasing my tail on that ever since. Let me make the necessary corrections. I'm going to make the schematic look like the Logisim Evolution circuit, and then I'm going to give this a shot again. Okay, I think I've got this here. Let me run through this quickly. That is finally working. I'm thrilled about that. Okay, and now that it's working, I do have a couple more changes I did have to make in the code, so I'm going to reflect those here. And my latch inverted output. Inverted output there. Inverted output there. Perfect. Well, that was a long, hard debugging session in order to get that code working. I am thrilled to have it working, but the challenge here is I've never used a 74HC or LS or any variety of a 123 multivibrator. So does my emulator faithfully represent the real life of putting it on a breadboard? I don't know. I also added a lot of debugging code into the emulator, this particular iteration of it. I'm going to leave that in place and commit those in case you want to go look at it and see just exactly what kind of code I put in for debugging this circuit in the emulator. Now I'm hoping that it will not take an entire video to put this on a breadboard and get it working, so if it doesn't, I do have a number of things that are sitting out in GitHub that I do need to clean up, and I will work on getting those accomplished as well, assuming that everything works properly. If you haven't yet, go check out the GitHub repository. I'll leave a link in the description, or I'll pop one up on the screen right here. We'll see you soon.